Hi everyone, I hope the audio and video quality is good. So let's wait for a few more seconds and we can get started. Cool. Let's get started. So I think this is the final lesson of Fast AI course. In this session, we'll be learning more about collaborative filtering and convolutional neural networks. And we will understand more on how embeddings work. So that's the main focus of today's session. So I already shared two notebooks. One is collaborative filtering, and the other one is convolutional neural network. You can run both on one on Kaggle and other on Google Colab for free. Maybe I'll show you how to run that. So I shared this notebook. Just click this one, and here I already created my copy. For you, it will show like copy and edit. Just click that. Once you click that, you can see some container like this. Here you can run your code. To run everything, you can click run all. To run one by one, you can click this button or shift enter. Like this. And you can see the environment, and it needs internet, and we also using GPUs. I think those information you can see it here. I think for this notebook, we are not using any GPU, and you can see the other details here. And to run Google Colab, what you can do is just click the link I sent it to you. So click this, and here you can run. Before running anything, click runtime, change runtime type. So I have Google Colab Pro version, but if you're using free, that's fine. You can still run the same notebook with GPUs. And here you can choose GPU, and you can choose standard, or if you have option as premium, you can choose premium. Otherwise, standard should be fine. Once you have clicked these things, you can click save. So this is like a high RAM or normal RAM. Once everything is done, you can click save. Then you can click connect. So currently it's creating a virtual environment for you to run the code. Yeah, it's connected, and you can see the RAM and other details here, GPU details and RAM here. I'm closing this because I have already opened the same here. I think that's all on how to get started. So now let's try to understand more about collaborative filtering models and interpret on embeddings. And we will also learn how embeddings is useful on natural language processing and tabular datasets. So that's the first half. And then the second half, we'll learn about convolutional neural network and what are some of the internal details in convolutional neural network. So I'm going to run one by one and explain what's going on. So we are using a dataset called movie lens. This movie lens has user details and movie details. So this is user ID and this is movie ID. And here you can see what rating this user provided for this movie as a rating here. So this is how this data looks like. And here we created the same data in a different format to understand um, many details like this. So if you see this one, the user 212, he has watched a few movies, but they didn't watch some other movies. Our task is to predict what rating this user going to provide for this movie, 49. And in 293, this user, what his rating will be for this movie, 49. So this is the task. And let's say we are getting some high rating, and then we can recommend those movies to that user. So that's the high level overview of the problem. So I think the last session we covered quite a few on how embeddings work. Maybe I'll quickly go through it. I used my own example in the last session, but this time let's use this example. So embeddings means it's like a random vector. It could be any length. It's up to us to define. So currently what we are doing is we are creating some random embeddings for this movie name. So Lost Skywalker. For this one, we are creating three numbers, 0.98, 0.9, and minus 0.9. So we can, currently this is random, but we can assume this is like science fiction, very science fiction, and 0.9 very not old, and 0.9 is very action, and minus 0.9 is very not old. So here this is called latent factors. For latent factors, we are trying to interpret each latent factor, and let's say this is some user, and let's assume this user likes science fiction movie. So we are assigning some high number for that user, and this user likes very action movie. So we are assigning some high number, and let's say this user not like old movies. So that's why it's minus 0.6. Then let's do some dot product. So if you do a dot product, we'll get a high number like 2.14, so which is good. So let's say there is another movie, Casablanca. So this Casablanca is, I think the first one is science fiction. Okay. This Casablanca, this movie is not a science fiction. So there is a negative number, minus 0.99. And this movie is not very action. So that's why it's minus 0.3. And this movie is very not old. I think it's a very old movie. That's why it's positive number. So now let's see whether our user with this taste likes this movie or not. To find that, let's do a dot product. So in dot product, we found that this is minus 1.611. In this case, we recommend movie this one to that user, not this movie. So this is like a high level understanding of how embeddings work. So embeddings are just a random vector with 550 some numbers. Okay. So here what we are doing is we know what are the uses. Here we are displaying few uses, and here we are displaying few movies. For each user, we randomly assign 5 vector number. So these are like 5 numbers for each user, and for each movie, we are assigning 5 number. Then we do a dot product. After doing dot product, we will have some prediction for each entry. Okay. Then what we do is we know the truth based on what user has already provided as a rating, like here. Then we find our prediction, which is a dot product. Then we try to compare our prediction with rating. Then we consider that as a mean square error loss. Then we optimize the network to reduce the loss. So what do you mean by optimize the network is we learn these embedding vectors during training. So initially they are very random numbers, but during model training, these numbers will be updated so that the error will be less. So that's the whole process. So now we are going to train a model. So we are loading the data set. And this is movie names, and we are going to merge this with our rating dataset so that we can interpret what each movie means. So once this is done, we are going to train the model. Before training the model, we need data loaders. Uh, for data loaders, we are using Collab data loaders, and ours is data frame. So we are using dot from df, and this is our data frame. And we need to mention what is our title. So this Collab data loaders assume a few things like user, movie, rating, then item name you can provide. Then here we are trying to create some embeddings ourselves. So we know the number of users from the user details, and we know number of movies from title. Then we are creating 5 random numbers for each movie and 5 random numbers for each user. And you can see the shape. And this is how the user factors look like. So this is user 0. His numbers are this. And you can see user 1. Her numbers are like this. So this is we manually creating embeddings. But you can also use embedding class to do the same. So this is also very similar. I think the last session we tried to understand how to get some details. So this is how you get. So now we are creating a one-hot encoding. So here, this one-hot encoding number of users, we are choosing 3. So that's why for user 3, 0, 1, 2, 3, we are setting 1, remaining as 0. This is one-hot encoding. And let's say you want to choose user 3's embedding details. You can do a dot product, like a matrix multiplication. If you do a matrix multiplication, you will get the user's details. So why we are doing this is, this is just a lookup. This is like lookup. But while creating deep learning layers, we cannot design a lookup, but you can design a lookup like this. We can do lots of matrix multiplications. So that's why we are doing like in this way. Now we are going to create a collaborative filtering from scratch. So collaborative filtering, what we are doing is for each user, we are creating some random vector. And for each movie, we are creating some random vector. Then we are just doing a dot product, like what we seen at the top, like Casablanca and Lost Skywalker. We created some random number. Then we did a dot product. We are doing similar things here. For all the users and for all the movies, we are doing multiplication. Then we are summing. So this is like a dot product for each user with all the movies. So this is our model, which is just a dot product. And we are mentioning the random vector should be 50. And to train the model, we are providing data loaders, which is our data set. Then we are providing the model, which is dot product. And our loss function is mean square error loss. We are training the model. So let's wait for a few seconds. You can see the loss is converging. Okay, so initially the loss is quite high, and then after training it converged. So yeah, let's do that. So here what we are doing is we are adding one more thing. So instead of just making a prediction, if you see our problem, the ratings are 1 to 5. So we don't need any number greater than 5 and we don't need any number less than 1. So to do that, we can use something like this one, y range. We can set a y range 0 to 5.5. It could be 0.5 to 5.5. It's up to you. So here Jeremy used 0 to 5.5. So whatever output we are getting, and we are trying to make sure it's in range 0 to 5.5. So that's what our prediction doing here. Then we are training one more time. So initially the loss is 0.88. Let's see the loss converge or not. Okay. So you can see the training loss is 0.39. Previously it's 0.77 and 0.88. Here it's close, 0.87. So this is like a good start, but we are trying to add few more things here. So if you see our previous model, we only have weights. We don't have any bias for each user and we don't have any bias for each movie. So sometimes some user always likes to give high rating for all the movies. And in some cases, some movies will be always high rated. In that case, to make the model train faster and converge faster, we can set a bias for each movie and a bias for each user. So that's what we are going to do. For each user, we are setting a bias, and for each movie, we are setting a bias. Then we are training the model one more time. Did our second fit one cycle knows the result of the first? No, it does not know the result of the first model because we are creating two different models. The first one is dot product, and the second model is dot product bias, which is one I'm doing right away. And this is dot product, and the previous one is, this is also dot product, learn fit one cycle, but we reinitialize here. So those are like two different models. So you can see dot product with y range, and the previous one just a dot product. So those two are different models, and we are not carrying any learned information from each models. Thanks, team. Okay, I think after adding dot product bias, we are getting 0.89. It didn't improve too much. Yeah. So now what we can do is we can introduce weight decay. So weight decay means, let's say let's say we have some weights and we have some biases. We mainly focus on weights. Let's say some weights are really high. In that case, what we need to do is we need to reduce the impact of the weights. So that what we can do is we can introduce new things, like for each weights, we take a square and we sum everything. Then we introduce a learning rate. This is like 0.01, some number like this. So that this makes sure your weights are not too high, so that it avoids overfitting. So to implement this, we can just mention weight decay equal to some number, which is this number, and it will implement automatically in the fit one cycle. So weight decay can be implemented in two ways. One is we can add parameters square, and we multiply by with some constant term, weight decay in loss. Otherwise, we can also do the same thing in parameters, because anyways, we are going to take derivative of parameter with, sorry, derivative of loss with respect to parameter. So if you are taking derivative of this one, which is same as parameter square is 2 multiplied by parameter. So instead of doing it here, you can also do in the gradient. There are two ways to implement. Yeah, I think after introducing weight decay, our model is really good. So previously it was like 0.89, 0.87, 0.88, but after introducing weight decay, we got 0.82, which is really good. So for collaborative filtering, this is what you usually do. Like you can start with some dot product bias, and then you can train a model. So now I think if you see one of our model, we are using embedding class. So this is embedding class. This comes from Fastai. Fastai uses Pytorch embeddings, nn.embedding. So now what we are going to do is, instead of using those embeddings from Fastai or Pytorch library, we are going to create one ourselves to know how it works. So that's what we are going to do now. So first of all, here I'm creating some class, and I'm using nn.module as a superclass. And here I'm doing like just a variable with torch.once. Then I'm asking the parameters. If you see this one, the parameter is empty. So there are no parameters here. So to get some parameter, you need to wrap your variable inside nn.parameter. So once you do that, you can get, you can see this is treated as parameter, which means you can back propagate and calculate the gradient. Otherwise, we cannot calculate the gradient. Whatever you wrap inside nn.parameter, we can calculate the gradient. You can see records grad equal to true. So this is one way to create. Other way is you can also use nn.linear module. So if you use that, it will automatically uses recurse grad equal to true. So you can see it here. So nn.linear, you can get the parameters. And if you check the weight, which is a parameter, and also here we don't need bias, but if you are asking bias, that is also a parameter. Cool. So here we are writing a function, create params. Whatever you size, you give the size, it's creating a Gaussian distribution of mean 0 and standard deviation 0.01. So now what we are doing here is, instead of using embedding a layer, maybe I'll show you the previous one. Yeah, here you can see embedding layer. Here also you can see embeddings, embeddings, embeddings. So what we are going to do is we are going to replace this with our own embedding function. So you can see it here. Instead of using embedding, we are using create params, and we are passing number of users and number of factors. The same way we are creating user factors, user bias, movie factors, and movie bias. Let's do that. Okay. So now we are going to train a model. So you can expect similar result of previous one. This is dot product bias, and let's see our previous dot product bias results. So dot product bias, we are getting 0.82 using embedding layer. Now we replicated embedding layer by ourselves, and we are training a model, and you will get similar results. So let's wait for a few seconds. So you can see we are getting similar results. So, and we replicate the embeddings by ourselves. So now we can try to interpret the embeddings and biases. So we are grabbing all the movie bias, and this is the movie bias. All the movie bias is grabbed as a vector. Then we are sorting and finding the top five numbers. In this case, the five numbers are this. For this movie, the user always, I think this is org sort. I think these are like low bias. So let's see the explanations. Yeah, lowest values. So this org sort is like lowest to highest, and we are asking first five. Maybe let's also try to find last five. So for these movies, the user always gives high rating. I think these are very good movies. People always give high rating for these movies, and for these movies, this movie always get like low rating. So that's what this bias means. So it's good to interpret the bias. Yeah, here you can see it. These are like last five movies. So now we are going to visualize the weights. So if you see, for each movie, we have 50 vectors. So we cannot visualize 50 vectors, but what we have done here is we used principal component analysis to convert those 50 vectors to three numbers for each movie. Then we can plot first two axes. So this is 3 dimension, and we are plotting first two axes. So you can see it here, factor 0, factor 1, and factor 2. I think here Jeremy plotted first and third, so that you can see some difference. So movies that are very similar, they are grouped together. Yeah, you can spend some time on this. So I think so far what we have learned is how to create embeddings and how to use Collab Learner by writing lots of classes. But generally we don't do like that. We normally use Collab Learner, and here you can pass number of factors, and here you can mention what is your Y range. That's it. So you don't need to write lots and lots of lines to implement the same thing. You can use Collab Learner, and then we train a model, and you will get similar results. I think so far we have covered data, dot product, latent factors, collab data loaders, embeddings, sigmoid range, and how to interpret the model, which is embeddings bias. And there is embedding distance. We will see that here. Okay. So yeah, we are getting very similar results. So with just one line of code, we are trained a neural network. Yeah, this is like a dot product model, and you can see the model here, which is same as our previous model, embedding dot bias. This learn is embedding dot bias. Same results. So now what we are doing here is we are trying to find the closest movie for some movie. Let's say you want to know what is the closest movie for this one. Based on the embedding distance, we can find which is closer. So for this movie, we are getting 12 Angry Men. So those are like very close movies. I haven't watched both, so I'm not familiar with these. You can interpret. Okay, so now what we are doing here is, so far we have seen only these two things. user factor, item factor, and we do a dot product. But now what we are doing here is, in addition to these things, we are adding one more layer after these dot product. So you can see this is like a neural network. We can create many layers so that it will learn some complex patterns by analyzing user embeddings and item embeddings. So this is Collab neural network. We are writing some class by ourselves, and let's train the model. So if you see this one, we need to mention some user size. We need to mention some item size, but there is a way to find that. Previously, we have set everything as 50 and 50, but there are some clever ways to do that. If you use get embedding sizes, and it will automatically tell you what is the size of the user and what is the size of the movies. So you can see some explanations here. Okay. So in this case, it didn't help too much. We are getting 0.88, but our previous model, we got like 0.82. So neural network didn't help in this case. So we have written some class for training the neural network, but you no need to do that. You can directly use Collab learner, and you can pass use neural network equal to true, and then you can create your own layers. So this is, I'm creating two layers, one layer with 100 neurons and the second layer with 50 neurons. So it's training. So how is Collab learner different to normal learner? Um, you can see it here. Collab learner is what we have created so far. So if you see this Collab learner, this is just a dot product with bias. Maybe maybe I'll print this learn dot model. So this is embedding neural network, and if you see the previous ones, let's go back here, learn.model, which is embedding.bias. So this Collab learner is just embedding.bias, which is what we have seen here. Yeah, this is our model. So instead of writing all these lines, if you use Collab learner, it uses this code. So both are same. So dot product with bias. I hope that answers your question. Thanks, team. Okay. I think we are pretty much done. So we learned how to train a Collab neural network, Collab learner, collaborative filtering model using few approaches. One is just a dot product, and the second one is dot product with bias. Then we used neural network, and also we learned how to create our own embeddings. And then we learned about how to interpret the embeddings, like what is embedding bias and what is embedding weights, how to convert 50 dimension to 3 dimension and visualize it, and how to use embedding distance to find the closest related movies. Yeah, you can maybe I already shared this notebook with you all. You can run and maybe you can read everything and understand more. So this is one of the best way to learn. So now I'm going to move to convolutions. So far in a lot of previous sessions, we have seen some CNN-based, ResNet-based models. So in this session, we will try to understand more about how convolution works and what's going on in each model. So we will learn those things in this session. So especially, maybe before going to convolution neural network, let me talk about embeddings in NLP and tabular. So let's talk about NLP first. Okay, maybe let me add here. So NLP. So let's say a sentence, I like this movie. And here what we do is for each word, we assign some random vector, which is embeddings. For example, I can be represented using 0.3, 0.2, minus 0.11 like this. So this is very similar to embeddings. This is embedding, that's all. So I like this movie. For each word, we are assigning some vector, and then we use that to do model training. So the embeddings is useful in NLP. If you see our previous sessions, we have done some NLP with embeddings. So in NLP, we use embeddings. So this is the relationship between embeddings and NLP. And for tabular datasets, so in tabular datasets, we usually have two things, continuous features and categorical features. So let's say for categorical features, let's say maybe city. So Brisbane can be represented using some vector, and Melbourne can be represented using some vector, and Sydney can be represented with some vector. Then during model training, those random numbers will be automatically changed to reduce the loss. So embeddings is helpful in tabular datasets too. I think with this, we can move to convolutions. Let's check questions. Okay, thanks, Jim. Okay, so now we are going to learn about convolutions. So I already shared this notebook with you all. You can click runtime, change runtime type. You can choose GPU. And if you have options to choose more, you can choose your own things. Then click save. Once this is done, you can click connect. So I already connected. Otherwise, you can see a button like connect. If you click connect, you can run code like this. To see what GPU I have got, maybe in SMI, I have chosen some basic GPU, so it should be D4. Yeah, D4. Recently, Google Collab Pro Plus introduced some advanced GPUs like A100, and to get those, change runtime type, choose premium GPUs. For this session, it's not needed, so I'm using with basic ones. Okay. So now what we are doing, let's say we are trying to understand convolutions first. What is convolution operator? So let's say this is your image. So image is like normally some number. You can see if it's like black and white, you will see only one channel with some numbers. And if it's like a colored image, you can see three channel, red, green, blue, with each number. So in images, it's always numbers. You can see some numbers like this. Let's say you are doing some convolution operator here. So let's say this is our convolution, 3x3 convolution. So convolution is like a matrix, like a different numbers. So generally it's like a random number, but here we assign some number like 0.1 to 0.9. Then we are trying to find whether this convolution doing something here. What we do is, which is just a dot product. So you can see 10 multiplied by 0.1, then 11 multiplied by 0.2. And after multiplication, you add everything, which is like a dot product. Then you can see this is activated really well, which is 94.2. So this is how kernel works. So kernel, convolution, filter are same. So kernel is like a little matrix, such as 3 by 3, like this. So yeah. Okay, I think I need to run from top. So this will install all the required libraries to run these things. No thanks. Oh, okay. I need to run. It tries to connect to Google Drive. Let's do that. Hello. Okay. Okay. I think it's connected. Now let's run this. Okay. Now I can run this code. So here we are creating a kernel. And this is like a horizontal filter. I will explain this. So this is some image 3. So here what this is explaining is each if you see some image, it's all about numbers. That's what it's going here. So here we are doing some dot product. We are selecting 4 to 7, which is this area, and then we are trying to find top edge, which is this one, top edge. So top edge is like all minus at the top, then zeros in the middle, and 1 at the bottom. So in convolution, let's say this is your top edge. For each area, we are trying to do some calculations. So we will do some calculations here. Then we move to right. Then we move to the next one. Then we move to the bottom. So this is how you calculate some numbers. So you can see, so whenever there is a top edge, our top edge kernel activates. So you can see it clearly identifies the top edge. You can see some horizontal things. So this is left edge, and this activates some part of the image. And you can see it here. So this is, let's say this is your kernel. It's looking something in this area, then it's moving to the right, then it's moving to the down, then it's moving to the top, bottom right. So generally we have multiple kernels. Here we have like 3 by 3 kernel, 4 kernels. Left edge, top edge, diagonal edge, and diagonal edge. So there are 2 things. So we are using MNIST dataset. So this MNIST dataset has 10 output, 0 to 9 numbers. We are trying to identify the numbers. So here we are trying to find some vertical edges. And here we'll see what is strides and what is padding. So let's say you want to, maybe before talking about this one, let's talk about the previous one. So let's say this is the one. What you can do is you can do some calculation here and you will get this number. And then you move to this side and you get this number. Then you move to the bottom left and you get this number. Then you move to the bottom right and you get this number. So initially, if you see our original image, this is like 4x4, but this 4x4 converted to 2x2 output. So there is some loss there. So to avoid that, you can use padding. So padding means we introduce some, let's say this is our original image. Okay, let's say this is the original image. Padding means we introduce some zeros around the image so that our end result and the initial input, they are same shape. So we introduce some zeros around the border, then we calculate the dot products. So that's all about padding. Then the next thing is what is striding means. So if you see this one, we are starting here. Then instead of going to the here, we are moving to here. So this is stride 2 convolution. So stride 2 convolutions are useful for decreasing the size of our outputs. So stride 2 means you skip the next one and you go to the next one. So that's striding. So let's say this is A, B, C, D, E, F, G, H, J. Let's say this is your input image. And let's say alpha, beta, gamma, and delta. This is your kernel. First, you apply your kernel to this area and you calculate something. Then you apply your kernel to this area and you calculate something else. Then you apply your kernel to bottom left, you calculate something. Then you apply your kernel to bottom right, you calculate something. So whatever you're doing here, this is like a same as doing some matrix multiplication. Let's say you can write some matrix like this, alpha, beta, in this way. And if you do matrix multiplication with A to J, you will get the same output. So this is another way of looking what convolution is doing. But our convolutions are a little bit faster than matrix multiplications. I think we learned about kernel. Kernel is just a 3x3 vector, random numbers. And during model training, it can be meaningful. Then strides means, let's say stride equal to 2. Instead of going to the next one, you skip and you go to the next one. So padding means we add some zeros around the border so that input shape and output shape should be the same. So here we are creating some CNN, some symbol network. And in simple network, we use nn.linear, but in convolutional neural network, we use nn.con2d. You can mention the kernel size, padding, stride, everything here. Okay, so here we are creating many convolutional layers. Then we are training a model. Cool. You can see the shape of each layer. So this is MNIST. I think this is, yeah, we're getting pretty good accuracy. So let's say this is convolution 1 and this is convolution 2. So what's the relationship between convolution 1 and 2 is there is a concept called receptive fields, which means this convolution, this one, we are doing something, but this comes from the previous ones. So if you see the original image, so this area is almost very similar to those areas in the original image. So that's what a receptive field means. I think there is a better way to see that. Maybe this one. So let us say this is input image, and to we are doing something here, convolution one, to calculate this number. So this number comes from this area, and all these numbers here comes from this area. So this is how, even though the output dimension is small, still that number comes from the same area in the original image. So this is for color images. So black and white, we just have one channel, but for color images, we have three different channels: red, green, and blue. For color image, our kernel should be 3 channel 2. So instead of 3 by 3, what we do is we use 3 by 3 by 3. And you can see here. So let's use convolution and create a model. So this is trying to identify MNIST, and we are creating a basic simple neural network. Okay. With this simple network, we got like 82% accuracy. We just trained for only one epoch. And let's increase batch size and train more. I think so. If you see the session convolutions, it covered a few things, but lesson 13 it covers more. So that's why these things are not covered in the session, but we will learn that in some advanced sessions. So this is I'm directly using the book, but for now, learning these concepts should be fine. What is kernel, strides, padding, how to use CNN in color, which is it has 3 channels, so we need to create 3 different um, channels in kernels. Then what is receptive field? I think basically that's it. You can also go through this notebook and try to understand more on this. And we learned how to use CNN in the early sessions. We tried to understand what's going on in the CNN, like what kernel is doing, and what is receptive field, and what is strides, and what is padding. I think pretty much we are covered everything. With this, I'm going to end the session. See you all next week. Thanks, everyone.